So now let's talk about the linear time sorting. Okay. So the title of the section is quite attractive because we finally got some extremely sorting algorithms. Okay. And how can we achieve better performance that is as fast as a linear function compared to the all the sorting algorithms so far we know about, like merge, quick, and heap. They all have n times logarithm of them as the best performance, but somehow if the inputs satisfy some constraints, then we can basically achieve linear time efficiency. So in this section, we will talk about 3 sorting algorithms: the counting sort, radix sorts, and the bucket sort. Okay, they all have different types of constraints or limits on the input elements. Excuse me. So the first counting sort, the constraint it has is that all the input all the inputs elements are integers, and the integer value are within certain range. For example, within the range between 0 and k. Okay, and k is also an integer number. So when this k is bounded by the input length, right? The k cannot be infinitely big. Okay, then the total algorithm runs the algorithm runs in linear time. Okay, which is pretty good results for us. Okay, and because the inputs are integers, we can basically design an algorithm based on this idea. We can count for each input element. We count the number of elements that are less than these elements, x. Okay, so we will use this information to place the x directly into the position in the output. Now, k cannot be negative. K is a positive number. Okay. So, but if it's a negative number, we can basically normalize the inputs, right? We can basically add the same value at the like minusing by subtracting the minimal elements within the input sequence, so that all the elements are converted to a positive numbers. Okay. So yeah, let me state the ideas again. So for each element x, we simply need to count how many other elements are smaller than x, right? So that is a very useful heuristics. Say, if I have 10 input numbers, and for the number x in it, I found that there are 9 elements that are less than this number, that are less than x. Then of course, x is the largest element. So we need to put x into the last position of the output, right? So this is a quite straightforward idea. Then another example is the different numbers, 17 elements less than x, then x belongs to the output position, 18. Right? So quite straightforward thoughts. And let's look at the implementation of such an algorithm. So the input is a sequence, right? And this time we need 2 other arrays. So we need to in order to help store the results of the counting, and to store the elements as outputs. Okay, so we will need to have a new array called B. Okay, so this B is the same length as A, and the function is to hold the output. Okay, so finally we will return the values in B. And other than B, we need to have a C. Okay, so this C is interesting. Okay, so the capital C is for counts. Okay, it's for the word count. So it basically it's a temporary array that will be used to store the results of counting. Okay, and the range of C is from 0 to K for a reason. Okay, because we have the range, we have all the elements within A, they are ranged from 0 to K. Okay, so this C actually have K plus 1 elements, right? K plus 1 elements, and the index. This is a little special place here because our convention, our pseudocode convention for this course is from the 0 index, is from the 1 index, right? The first index is 1, but this time it's a little bit special because the condition, the input condition is that our elements ranges from 0 to K. So we will give it a special 0 index as the first element in C. Okay, it actually has K plus 1 elements in C. So this is how the counting sort looks like. So without diving into details, let's just look at the structure of it, right? It's one for loop, second for loop, third for loop, last for loop. Okay, and the first and the second, the first and the third for loop, they loop over 0 to K and 1 to K. So that is almost a big O of K, right? And for the second and the last for loop, they iterates from 1 to A dot length and A dot length down to 1. Okay, different order, but the same length. So that is around the big O of it. Okay, so that is obviously some linear time functions, right? It's no nested for loops. It's just four consecutive for loops. Okay, so what we are sure now is that it's a pretty efficient algorithm. Okay, so all we need to examine now is the correctness of it. Okay, and let's look at the next page. Okay, the first for loop is nothing fancy. It's just to initialize the array to all zeros. Okay, it iterates over 0 to K. Okay, the second for loop is a loop that iterates over all the elements in A, and A is our inputs. Okay, and what it does in this body is to look at each element in the input array, and if the value of that element is I, then we need to increment the corresponding elements Ci. Okay, so there's a nested structure here, nested brackets. So the index for the C is A of J. Okay, so we let J iterates over the A, right, over all positions of A, and we use the value AJ as the index for C. That is a valid operation because we are guaranteed that all the numbers in A are integer numbers. Okay, so an integer number can be an index, right? And also we first initialize the array C to have K plus 1 elements. So this A of J is always within the range of between 0 and K. Okay. So whenever we find an AJ, say we find some value, we will increment the count for that value by 1. Okay, so the C after this second for loop, the array C actually stores the counting information. It has the count for all unique values in the input element A. Okay. So after line 5, after the first 2 for loops are done, the element Ci should hold the number of input elements equal to I. Okay, and this I is for each integer from 0 to k. Okay, and let's look at the third for loop. Okay, so this time it iterates from 1 to k, from the second element in C until the last element in C. And what it does is to have this running summation. Okay, so this is a cumulative summation, which is to let Ci to be the value of current Ci plus the previous value. Okay, Ci plus Ci minus 1. And that is why we have C start from 1. Okay, because it's I minus 1 here. So the results of this third for loop, okay, actually has the meaning that now Ci actually stores how many elements are less than or equal to I. Okay, because it's a running sum. It sums up the previous cells to the current previous elements to the current elements in C. Okay, so it actually contains the information that we need, right? In the example that we say at the beginning is that we need to know how many other elements are less than to the current elements I, so that we can put I into the correct position. Okay, so now after the third for loop, we can finally use the last for loop to place the elements in A into the correct position of B within B. Okay, so now we have a triple nested structure in the last for loop. Okay, so J is from the last element to the first one in this reverse order. Okay, so later we will see why this reverse order will be critical. Okay, so but first we need to take out AJ. Okay, and AJ, as we know, it can be the index for C. So we will take C of AJ. Okay, so remember, C of AJ is now the number of other elements that are less than or equal to AJ. Okay, so we will use this positional information to copy AJ to the correct position of within B. Okay, and after this placing back to B operation is done, we need to decrease the elements, decrease the value of C of AJ by 1, because we have taken one element in A out and place it to B. Okay, and we will do this until we have gone through all the elements in A. All right. So I mean, if we want to understand the algorithm through this textual description, it will be not that straightforward. So we will basically first look at an example, and then you can go back to the slides to read about these descriptions again. All right. Let's look at an inputs like this. We have A's. All right. We have 8 elements. And the values, we can see that they are all integer numbers from 0. The smallest is 0 and the largest is 5. All right. And we initialize our C as like this by the first for loop. Okay. And now we need to think of what the results would be in C after the second for loop is done. Okay, So this second for loop is to iterate over all elements in A, and it lets the C of AJ plus 1 for each step, right? So after, like, for example, if J equals 1, right? When J equals 1, then AJ is 2, right? And that means we need to increment C2 by 1, right? Because we have met 1, 2 here. We need to increment C2 by 1. And in the second iteration, when J equals 2, AJ is 5, and that means we need to increment C5 by 1 because we have C1, 5. And then J equals 3, we need to increment C3 by 1, that is 1. And then J is 4, we have C0 by 1. And now we have J equals 5, and it's 2 again. So we need to increment C2 again. So now C2 will be 2. Okay, so after the second for loop is done, we will have something like this. Okay, we have C's that has all the counts for all the values in A has been stored here. So the zeros here means that there's no integer number 1 and integer number 4 within the original input sequence, right? There's only 2, there's only 3, right? There's only 0, only 5, but there's no 1 and 4. Okay, so I hope this meaning of 4C is clear now. All right, so, and after line 7, which is the third for loop, right? The third for loop is a running sum. It adds the current value with the previous value, right? Right, it's like adds the current value with the previous value. So after line 7, we will have C like this. Okay, the 2 will be the results of adding these two numbers, and the 4 will be results of adding 2 with this new 2, right? Which is the summation of all the elements before, which is 2 plus 0 plus 2. And the 7 is 2 plus 0 plus 2 plus 3, right? And the 8 is basically the numbers of all numbers, the number of all possible values in the input sequence A. Okay, so that is how we get the C before the last for loop. Okay, so let's look at the meanings for the C's again more closely. Okay, so the 7 here. Okay, so what does it mean? C7 equals 7. C3 equals 7. It means that there are 7 elements in A that has the values less than or equal to 3. Let's see if that's true. Okay, that's 1, 2, 3, 4, 5, 6, 7. Right, that is correct. And this C4 equals 7, which is similar meaning, right? There's 7 elements that are less than or equal to 4 because there's no 4 in A. And the C5 equals 8 means that there are 8 elements that are less than or equal to 5. Okay, so the meaning of C is also now clear. All right, so all we need to do is to use C to place the elements in A back to B, not back, but to a new place, to B. Okay. All right. Now what we are doing is mainly focusing on the for loops, the last for loop. Okay, because the order of the for loop is a decreasing order. It starts from the last elements, A.length, down to 1. Okay, it's a reversed order. And J equals 1 in the first iteration. So we need to look at AJ. right? What is the original value? The last element is 3, right? And then we need to refer to C of AJ, which is C3, right? Which is these elements. And it is 7, okay? This 7 is the new position of the elements that we need to place the 3 into B. Okay, it's the 7th element in B, right? Which means we need to copy the 3 here to B7. So the B will look like this after this copy is done. Okay, but remember, we need to decrement the values in C of AJ by 1 because we have taken 1, 3 out, and there should be 1 less 3 in the original A. Okay, so this 3 is copied to B, and C3 will be C3 will be 6 now. Okay, it will be no longer 7. Okay, because we have taken 1, 3 out. So now the C3 is 6, which means that in this updated elements sequence, there's only 6 elements that are less than or equal to 3. So the next 3 will be placed to the 6th position of B as well. Okay, so that is the first iteration. And let's go through all the remaining steps. Okay, so next step, the J will be 7, and AJ, the value will be 0, right? And the corresponding C value will be 2, right? So, which means we need to copy the 0 to the 2nd position, to the 2nd element of B, right? That's how we get B, okay? And decrementing C of AJ by having the value from 2 to 1, okay? And next iteration, we'll go through it more quickly, okay? We'll copy another 3, okay? So now since we have met the second 3 has the corresponding C equals 6. So this 6 means that we need to copy the 3 to the 6th position here. All right, and decrementing C of AJ as well. Okay, so I don't have all the steps printed out here, but it's okay if you would like to try it on the paper, right? So it's a very smartly designed algorithm, right? It will basically count how many elements are there that are less than or equal to the current elements, so that the relative positions of all the elements are decided. Okay, it's a very smart algorithm. Okay, so now let's look at these points. Why we need to have the sorting to be stable? Well, why we need to have the order to be reserved? And the main reason is to make sure the sorting is stable. Okay, so it's we will have the more or less the same results if we use the normal order, not the reversed order for the for loop. Okay, but the values, the elements of the identical values will not be in their relative orders will not be reserved in such a way. Okay, so we basically want to reserve the order that the first 3 is always before the second 3, and the second 3 is always before the third 3. Okay, we want to treat them as if they are different values, although they have as if they are different elements, although they have the same values. Okay, so this one-to-one mapping relationship is what we want. Okay, so the last elements will be placed here. Okay, the middle one will be placed in the middle. The first one will be remain the first. Okay, so this order, relative order, is reserved. But if we let the algorithm to go from that way, from left to right, so the first three will be this one. Okay, when we first met these three, it will be copied to the last elements, and the second will be the middle, right? But the last one will be the first one, copied back to first one. So the orders will be scrambled, and that is not what we want. In some cases, okay. In some, if it doesn't matter, then it's okay. But sometimes we want the relative orders to be preserved. All right. That is counting sorting. Okay, and in this page, I see a question. 0 to k. Yeah, because in this condition, we require that all the elements can arranges from 0 to k. Okay, so we have, in this particular example, we have all the elements ranges from 0 to 5. So we need to allocate 6 grids within C. Okay, 0, 1, 2, 3, 4, 5. Okay, for each of these possible integers in the original inputs. Okay, that is based on the requirements of the input numbers, because the input numbers have zeros. Okay. Yeah. So this is a special place for counting sorts. We can assume that the index for C can start at 0. Yeah, just in this style, which is different from the pseudocode convention that we are used to. Okay. Yeah, I think it can also be like CA to K whenever you have arbitrary values as the lower end and higher end. Yeah. All right. Let's go to the sorting time. The running time. So we have actually done this, right? If we combine all these linear for loops together, it will be basically big zeta of n plus k. And since that k is also bounded, right? When we assume that k is bounded, then the total running time is basically the big zeta of n. All right. That's the first type of linear time sorting algorithms. And let's quickly look at the second, okay, which is radix sorts. All right, so these sorts algorithm, again, has its own advantage, own constraints, okay? It's not like an unbounded, the input elements cannot be unbounded values. It's like we are sorting numbers with the fixed width, okay? And all the numbers, they belong to the n digits number. They have the n digit width, okay? So in this case, when this n digit requirement is placed to all the numbers, we can basically sort on the least significant digit, right? Because we have d digit, we can start from the first digit, okay? And then after the first digit is done, we will sort all the results on the second digit again, okay, until we have sorted all the significant digits, okay, until we have all the d digits already all sorted, okay. So here we need to make sure that all the digit sorts, the sorts that we used at each digit step is basically a stable sorting algorithm, which preserves the relative orders of the numbers that has the same values. Okay, so let's quickly look at this example. Okay, we have a bunch of 3-digit numbers. They all have the same width. Okay, It's like this. So by sorting over the least significant digits, we mean these last digits. Okay, so we sort all the numbers based on this digit, which means that the 9 here will be placed at this position. The second 9 will be placed at this position, right? Because the 9s are the largest numbers, right? But since the sort is a stable one, so the first 9 we encountered will still be the first one in the output sequence, and the second 9 will be the second. So their orders are not scrambled. And so is the order for this 7, right? The first 7 and the second 7. The 6 is here, 5 is here. Okay, so it's like a one-on-one mapping. So now we have this first round, the least significant digits sorting is done. All right, what will be the next? We sort over the second digit, but the input will be this intermediate result. Okay, we'll sort based on these results. So now if we look at the 5 here, 5 is the biggest one, right? 5 will be placed here. Actually, no, this is yeah, that's correct. But the first 5 is here. Yeah, the first 5 is here, and the third 5 will be here. Okay, their relative orders are preserved, and the smallest 2 is here. The second 2 is here, right? And the 3 will be here. And the second 3 will be here. All right, so their relative orders are preserved. Okay. And lastly is the third step, right? We can simply sort all the algorithms by looking at the first significant place, the first digit. Okay, so I'm not going to draw all the numbers, but you will see that we've got pretty nice sorting algorithms, and the actual values of these numbers are in exactly the sorted order, right? All these numbers. So this is a really fascinating way to solve all the numbers that has the fixed width. Okay, so it is important to make sure that the sorting algorithms, they are stable. If the orders are scrambled, like these 3 5s, if they are scrambled, right, if the orders are not preserved, then the sorting algorithm will not return the correct results. Okay, because the previous step information is not preserved, is not carried on to the next step. Okay, we want to carry on the next step from the previous digit to the next digit and to the final digit. Yeah. All right, let's look at the implementation real quick. So what we're going to show here is a pretty indirect way. Okay, so we assume that we have d digits for all the n elements in A, and we assume that 1 is the lowest digit and d is the highest order digit. So it's basically 2 lines of code. So it's quite this is a quite lazy implementation, right? It's just a description of the idea. Okay, but rather it's quite the idea is straightforward. So for each digit, we'll use some stable sort to sort the array A on digit I. Okay, so we are not going to show the detailed implementations because it's probably going to be very language specific, like how you organize the numbers in with same digit or with same width, right? It could be a 2D array in lower level languages like C, like we need to declare some 2-dimensional memory space. Yeah, so that's why we don't dive into the details. But all we need to do is that we need to make sure this is a sorting algorithm carried out for each step. Okay. So in terms of the running time, if the sorting algorithm that we use is the counting sort, right? Because we know that counting sort is a stable sort algorithm. So we can use the counting sort as the sorting algorithm for each step. Okay, so that is basically d times n plus k, right? And we can say that if the d is not very big value, if d is not changing, if d is not increasing, right? D is just a constant. So we can say this algorithm is just kind of a linear running time algorithm. All right, so we have the one last step to cover, which is bucket sort. Okay. So we have some sort of constraints placed to the bucket sort. And this time, the constraint is that we assume the inputs is not like an integer or from a formed by fixed width, but it's drawn from some uniform distributions. It's now a floating number, but within within a region with limited region. Okay. So we under this case, we'll have the average running time as linear function. Okay. So what we further assume that is we assume the inputs is actually generated by some random process. Okay. And this random process will distribute the elements uniformly and independently. Okay, so each element is not related to any elements in any previously drawn elements, and they all exist in a region from 0 to 1. Okay, so it's a small number from between 0 and 1. Okay, so what we can do, what this algorithm does, is to divide such a small interval from 0 to 1 into actually n equal sized subintervals. And in this case, we call them buckets. Okay, we have little buckets divided between 0 and 1. And what we will do next is to distribute the n input numbers. We will place them into the buckets, into the correct positions. Okay, so because all the numbers are randomly selected, are randomly drawn, we do not expect that many numbers will fall into the same buckets because it's a uniform distribution. The distribution should be quite a uniform shape, right? And then after this distribution, we will sort numbers in each bucket and then go through the buckets in order by listing the elements in each. Okay. The sorting is actually done within each bucket. Okay. And we know another information about the buckets is that those the relative positions of those buckets, they are ordinal, right? The bucket from 0 to 0.1 is smaller than the elements in the bucket from 0.1 to 0.2, right? That is for sure, because all the numbers are within the region from 0 to 1, and we have placed all the elements into the corrected buckets accordingly. Okay, so as long as we have sorted all the elements in each bucket, we can quickly listing them together to get the final results. All right, let's look at the algorithm. So this time we will also allocate some new memory space, which is called B. Okay, but first of all, we need to assume that all the elements in A are bounded by 0 and 1, between 0 and 1. Okay, And 0 and 1, the B in the B elements, in the B array, we also assume that the index starts from 0 to n minus 1. Okay, so this is a special because this is also decided by the boundary 0. Okay, we have made such a constraint that all the elements in A can have the value 0. Okay, so the index 0 is just for the convenience to memory the position of the bucket. Okay, so the first for loop is just an initialization. Right, this is just initialization. It's just for each bucket, we'll make it a empty list. Okay, so let's look at the next slide. The critical step is actually this distribution step from line 5 to line 6. Okay, so now we go through all the elements from 1 to n in A. Okay, we need to place the element AI into the correct bucket. Right, the correct bucket is decided by this index, and this index is the results of flooring applied to n times A of I, which is the element A. Okay, right, because we have n buckets, so the results of n times AI is a number that's between 0 and n minus 1, right? And we need to make it a floor so that the index is between 0 and minus 1. So for example, in this case, A equals 1 means that we need to use 10 times A1, and A1 is a small number, which is 0.78. So 10 times 0.78 will 7.8 is 7.8, and the floor rounded to 7. Okay, so which means the A needs to be placed at the seventh position. Okay, because it's a list, we will insert A1 to the list of B7. Okay, and the next one, we need to go to the second A2, right? A2 is 0.17, and the results of this flooring will result in A1. So A2 will be inserted to B1. Okay, and A3 will do the same thing, which is 3, right? So basically, after we have gone through all the elements in A, the elements will now exist in B, but into these small buckets. Okay, each linked list is a bucket here. Each linked list is a bucket. All right. All right. So we need to use the last for loop to sort all the elements in BI. Okay, in each bucket, and the example code that you use here, which is a choice from the textbook, is to use insert and sort. Okay, so it's basically not, I would say, not theoretically, it's not the ideal one, because the insert and sort is not will have some running time issue when the input is mostly is the worst case, right? But we can see that its average case is also not as efficient as merge sorts or quick sorts. Yeah, but the further detailed analysis of the algorithm will say that after we have distributed all the elements into little buckets, this insert and sort will basically run as fast as other more efficient algorithms. Okay, so but that is not a required content for knowing why this is the case. Okay, so all we need to know is that we need to sort all the elements within each bucket. Okay, and after the sorting are done, we can concatenate all the elements within all the lists within these buckets. Okay, so it's basically a convention. we use insertion sorts to sort each linked list. Okay, of course we can use faster sorting algorithms, but the textbook tells us that even if we're using insertion sorts, the total running time is still big O of n. Okay, so this is something that the textbook has showed that we have when we have a random number as the size of the buckets, and the expected running time would be approaching a linear, would approach a linear function. All right. So that's so much for the insertion. No, for the linear time sorting algorithms. And we talked about these three types of linear time running algorithms. And if we compare it with those quicksort, heap sort, merge sort, insertion sort, these are basically comparison-based algorithms by comparing the elements, by comparing the magnitudes of the elements in a sequence. But these linear time sorting algorithms is not based on direct comparison, but it's based on some comparison of partially the value or partially the representation of the inputs elements. Okay, so I hope this table will be helpful for you to understand the running times for all the algorithms that we have covered so far. Right, so I think that's so much for the lecture today. And for the next Thursdays, that is 2 days later, we're gonna have a review for the previous contents. We will talk about the midterm, like the scope, like the what will be covered, what will not be covered in the first midterm. We'll talk about that in the next lecture. We can also go through some questions in our assignments. All right. Okay, so if there are no questions now, I will stop.